Hi, my name is Arik Ermsaus. I'm a PhD student at Humboldt University in Berlin, Germany, and I participated with my colleague Patrick Schäfer at the multi-dataset time series anomaly detection competition, and we ranked 7. In this video, I'm going to give a brief overview of our approach. I'll begin by talking about the evolution of our approach. The main idea that we used was a 5 nearest neighbor distance profile with time series subsequences. So given the time series that contains an anomaly, we split this time series into overlapping subsequences. And then for each of the subsequences, we calculate the 5 nearest neighbor and save the corresponding distance in a distance profile. And then the idea is that the subsequence with the highest distance is the anomalous subsequence that we search for, and we simply report the subsequence that has the highest distance as the anomaly. Using this simple approach, we scored around 50% accuracy. And what we then started doing is we added pre-processing steps to the time series and post-processing steps to the resulting distance profile, and were able to increase our score to around about 73%. At this point here, we stagnated and said, okay, we have to do something different. So we threw away all the pre and post-processing steps and kept the idea of the 5 nearest neighbor distance, but changed it a little bit around. What we did is that instead of calculating the distances on the subsequences directly, we first transformed the subsequences using the rocket transform, and then calculated the distance on the transformed subsequences. We then also added feature selection and feature normalization. And as one of the last steps, we also added ensembling of multiple distance profiles, and were able to then increase our score to around about 84.4%. On this next slide here, you can see an overview of the entire workflow. So we start here with the time series, and we also calculate the period size of the time series. We do this by calculating the Fourier transformation of the time series, and then simply extract the most dominant frequency as the period of the time series, and we then take half of this period as a window size in the windowing process. We resample the time series to 50,000 data points if it is larger than 50,000 data points, simply because the nearest neighbor computation becomes infeasible for larger time series given our computational resources. And then we window the time series into the overlapping subsequences. Given these subsequences, we then calculate the rocket features. Maybe as a brief summary, rocket is a predefined amount of random convolutional kernels, and these convolutional kernels are then convolved with a given subsequence. And then 2 statistics are calculated from each of the random convolutions. So you then basically end up with quite a large feature vector that represents one subsequence. Given these feature vectors for all the subsequences, we applied feature selection and feature normalization, and then calculated the actual 5 nearest neighbor distance profile. Such a profile then looks similar to this one. We have this time series here where we have an anomaly at this location, and the distance profile spikes at this point. So we can simply extract this global maximum and report it as the anomaly. In the next few slides, I'm going to go a little bit more into depth about each of the steps here. The first interesting A major step is the feature extraction with Rocket. So given the time series subsequences, we want to calculate the Rocket features. What we did is we actually calculated 2000 Rocket features for the raw subsequences and also 2000 Rocket features for the Z-normalized subsequences. And then we concatenated these 4000 features into one feature vector. The idea of using the raw and Z-normalized subsequences is that the raw subsequences reflect point outliers in the time series, and the Z-normalized subsequences are more able to reflect subsequences outliers. And using the concatenation of both, you then get a representation that reflects both of these types of anomalies. Having these features, this is now quite a large feature space. So the idea is to reduce that feature space to the most important ones. And we did this by using 2000 features with minimal variance per subsequence. So we basically reduced the 4000 feature vector to a 2000 feature vector. And the idea of using minimal variance is that most of the time series reflects one reoccurring pattern. So a good feature should have low variance because the time series is mostly the same pattern. And then only at one specific location, this pattern deviates the anomaly. And we would then expect that these features also deviate. And the distance profile is able to reflect that. And the distance profile is then the last major step in our pipeline, where we have the windows, calculated the Rocket features, reduce the Rocket features, and then are actually able to calculate the 5 nearest neighbor distance profile, which looks similar to this one. In an optimal instance, we have our time series here. We see a clear anomaly, and the distance profile then spikes at this anomaly, and we can simply extract this local maxima, global maxima. As a last step that we applied is ensembling. We calculated the entire pipeline that I just presented not once, but 3 times for different window sizes. One time for the period size half, another time for the period size, and last time for 2 times the period size. And then we get 3 distance profiles and simply average these profiles into one and then extract the global maxima position. This increases accuracy and brings more stable results. In summation, the lessons learned for us in this competition were that using a good feature representation, like for example the Rocket features, can actually replace a lot of pre-processing and post-processing steps, and that using raw and Z-normalized subsequences makes quite a difference because you are able to reflect 2 times of anomalies in your feature space. And also, maybe as a last note, that ensembling your distance profiles or using really well-chosen window size makes quite a difference. If you have further questions, please send us an email. I hope that you liked this talk, and I wish you a good day. Goodbye.